Before moving on to the last type of operation, which is very interesting and which is more practically used. Okay, this is a case with sample and hold. Okay, in case of sample and hold, as I might have quoted in the yesterday session, this utilizes a transistor to sample which will act as a switch, and a capacitor to hold its value. Okay, a transistor along with a capacitor will act as sample and hold circuits. First we will take mathematical route, then I'll talk about what would be the actual circuit content in such operations. Okay, so the concept behind this, okay, this is a kind of a conceptual treat. Then we'll go with a analytical treat. With a conceptual treatment, I can say you have x of t multiplied with x delta of t in case of impulse sampling. So this was the case with impulse sampling, where we multiplied original information bearing signal with a train of impulses. Now the sample and hold operation is that method where it tries to multiply with these x of t into x delta of t in a frequency domain with the rectangular pulse, or in other words I can say the xs of t, the sampled version of this, is nothing but convolution in time domain of a rectangular pulse with x of t multiplied with x delta of t. We'll see how will it how will it look like, where p of t is simply a rectangular pulse. Okay, it's simply a rectangular pulse of a finite duration. The duration is nothing but Ts. Okay, so this will result in flat top samples. Okay, in earlier case, in case of natural sampling, as you might have seen, the amplitudes of these all sampled versions were in natural or in accordance with your information bearing signal. If I try to join all these curves, it would have represented your original information bearing signal itself. But this is it's not possible to replicate the original information bearing signal for a long duration of time, and hence we'll try to flat these amplitudes of these all rectangular pulses, and hence is the case with the sample and hold operation. And hence you will see in the diagrammatical representation of this why this is called as flat top sampling. Okay, anyway, we'll just cover the conceptual treatment of this by taking Fourier transform of both the sides. You know that convolution in time will convert into multiplication in frequency domain. This is simply p of f multiplied by the Fourier transform of x of t, and we know to represent x delta of t, we have represented in terms of Fourier series, which is running from minus infinity to infinity, delta of t minus nts. This is nothing but p of f, where Fourier transform of x of t is x of f, and again in turn here it's a multiplication of two time domain functions, and in frequency domain it will be a convolution of these two frequency domain representations. So this will be x of f convoluted with what's the Fourier transform of delta of t minus nts. This is 1 over ts summation, it's another impulse train as we have seen, delta of f minus nfs. Okay, and using your frequency convolution property, we know that this is simply p of f. I can take this 1 over ts outside, and this is simply summation n over minus infinity to infinity x of f minus NFS. So it's very similar to the previous version or the ideal sampling case, but here the amplitude is multiplied with the rectangular pulse of width TS, which is represented as P of F here. Okay, so this P of F will be of the form of something like TS sync of FTS. Okay, so as you know, the rectangular pulse whose Fourier transform will be a sinc function, so whose amplitude of the sampled version will mimic the case with the natural sampling. But unlike the natural sampling, the amplitudes of those samples will not be in accordance with the message signal, but all those will be flat tops. What I mean by this, okay, to have an analytical understanding of this, we'll try to have a sample and hold circuit itself. Okay, so this would be a little interesting as part of your this operation is concerned. As I told, this actually comes with sampling, which is like a switching operation, and holding with respect to a capacitor. So a transistor which I take here, so if I take an NMOS, okay, with its gate applied to say a control voltage, whose is actually the control voltage are all these pulses, okay, and to its drain, okay, this is your drain, this is your source, this is your gate. To its drain, I'll apply the input voltage. Okay, this is my X of t. Okay, then this will sample, I mean it will give you samples at the source output, but I need to hold this. I'll connect a capacitor to hold its information. That is not enough. I need to take this at the output, for which I will connect to an op amp with its non-inverting terminal. Okay, so it's a simple circuit where it is connected to the output terminal V out. Okay, this I can connect here. Okay, this is your resistance R, which are identical to each other, and in order to derive the output, I need to have a load resistor. Okay, so this is fed back, and as you can see, this op amp acts as, so this complete op amp in this configuration, okay, I can divide this into three parts. Okay, so this is for sampling, this is for holding, and this is nothing but your non-inverting voltage buffer. You have an NMOS connected to a capacitor. The basic job of NMOS or the transistor is to the gate of the NMOS is connected to a control voltage, which is typically a pulsed waveform, and the drain of the NMOS is connected to the input analog signal, which is a continuous wave. And as you know, as long as the pulse is on, for the on duration, it passes the input signal, and for the off it doesn't pass. I mean, switch is closed. So basically NMOS acts as a switch. So it acts as a switch, and capacitor acts as the storage of the signal which is passed from drain to source. Okay, so if you want to brief out the working principle of this basic circuit, whenever the MOSFET is conducting, which acts as a closed switch, this will lead to the charging of the capacitor, which is present in the circuit with the input applied voltage. So whatever is the input applied voltage, the capacitor tries to charge with that amplitude. The charging duration of the capacitor, so whatever the duration it takes to charge the capacitor, is said to be the sampling interval. So Ts is nothing but the charging duration of the capacitor, okay, which is nothing but your sampling period. Okay, and at that time the overall input appears at the output across the capacitor. As we can see in this circuit, the signal at the source of the MOSFET is fed to the source is fed to the non-inverting terminal of the op amp through a resistor R, and also the output of the op amp is provided at the inverting terminal. The inverting terminal of the op amp is connected to the output through across a load resistor. So it basically acts as a non-inverting voltage follower. Okay, it's just a buffer, acts as a buffer. The purpose of attaching this voltage follower at the source end of the NMOS is basically whenever the control voltage is off, whenever there is no supply to the gate, the transistor is turned off, so switch is open. So when there is no signal passing from drain to source, the amount of storage or the amount of voltage presiding in capacitor tries to discharge. So it tries to find paths on its left and on its right. It cannot discharge on its left because of the source terminal of the NMOS itself, and on its right, since it's a non-inverting voltage follower, it will offer a high input impedance, and hence it will retain its charge, or it will store the amount of information which is passed during the on time. It will retain its original information until the next the on time of control voltage appears. Okay, that's the reason the non-inverting voltage follower is connected to the source end of this. Okay, so then hence this keeps on repeating, where the voltage across the capacitor is kept on extracted at V out during the on period of the pulse. So if you want to draw a graph which depicts the working, so this is your original V in, which is applied to the drain end of the MOS, and of course the sample is taken as an impulse here, but practically it is a small pulse. Okay, so here delta t, or the duration of the on time, is considered to be very less. Okay, it takes the sample at uniform intervals of duration, and at the output, this is at the output, V out is actually it will hold its voltage value. You can check the amplitude of this output voltage at all these values. As you can observe, all these will be representing the holding of the value or the charge of the capacitor until next cycle of on appears at the gate of the NMOS. So all these amplitudes of these pulses are flat, and hence it is also termed as flat top sampling when compared to natural, where the natural sampling was mimicking the actual amplitude variations of the input voltage itself. Okay, so this was with the continuation of last session. Also, there's a famous IC which is known as LF398, which is predominantly used again in digital communication theory, where it comes with very similar to op amp structure, where you need to just feed V in and control signal and connect a capacitor at the output, and you can try to change for the duration of time on the x-axis. You can try to plot the graph which will mimic the flat top sampling. As you can see, this is the duration where the capacitor charges, and it will hold its value as it is until the next on cycle comes. Again, it tries to mimic or the charge with respect to the input signal, and again it goes flat, and so on, and as it continues with several on and off cycles. Okay, this is how you can understand the circuit of sample and hold. Okay, all right, so this is a small picture I have got you. This is one of the tools that I use at my end. This is a tool called as Camtasia, which I use for my video processing. As you can see, these are the bit rates or the sampling frequencies which are available in my tool. I just wanted to have a feel about it. Usually in digital CDs or speech processing applications, your bit rates usually earlier days, when the audio used to come on compact discs or CDs, the sampling rate was around 48 kilobits per second. So 48,000 bits per second was the sampling rate. Now, since with the advancement of all digital technologies, we have got our MP3s. Whatever downloads that you do or you hear online will be at least having 128 kilobits per second of the sampling rates. But it can go up to 256, 320, and up to the 1024 kilobits per second. Only that will increase is with respect to their spaces. Like it depends on what is the bit rate of the music system or music that have been used for sampling. The higher the bit rate, the more amount of the space that it's going to consume. Lower the bit rate, less amount, but definitely the quality of the sound will not be good. Say for high definition televisions or high definition transmissions, definitely you will go beyond 512 kbps or 1024 kbps for such kind of applications. Okay, I just wanted to have the actual ranges of these rates. What do you mean by that? Anyway, just moving ahead, I'll just pick up next part of this. As I told, I'll try to talk something about aliasing. Okay, so aliasing, as I told, is nothing but this is the crosstalk between adjacent samples. Okay, so the derivation of the sampling theorem, whatever we did with respect to 3 types of sampling techniques, all describe all those descriptions based on the assumption that the signal is strictly band limited. In practical scenarios, as I might have quoted yesterday's class, in reality, you can say that the message signals or the information signals are not band limited. Okay, so even if you keep your sampling rate or sampling frequency much greater than twice of the maximum frequency content in the information signal, the tail of all these original information signals, they'll try to crosstalk with the adjacent samples. So this is not just a sufficient condition as per as the Nyquist theorem for the signals in reality where they are not band limited. Okay, so aliasing will happen in spite of keeping a sampling rate much greater than twice of FM. But also aliasing will happen obviously in case of undersampling, where you keep your sampling rate by mistake less than twice of maximum frequency. So it's very important to identify the maximum frequency content in the information signal using your spectrum analyzer or any other tools which will give you frequency content of a signal, and keep your sampling rate much higher than twice of that. Okay, so if say if you have oversampling, or we have going with the oversampling to make to nullify the aliasing, but in reality, if there are tails which are unwanted signal part which is affecting the adjacent sample, then we need to correct that aliasing, or we need to negate the effect of aliasing in our system. So to do that, to reduce the effect of aliasing, so this is what is the basic block of sampling. After sampling, we go with quantization. Okay, sampling will give you discretization of the signal in time domain. Quantization block will give you the output, the discrete in its amplitude. Okay, so this the output is discrete in time. So this is discrete in time. This will give you discrete in amplitude. Okay, before sampling, if there is if you want to say negate the effect of aliasing, we need to perform an extra operation which should be passed through a filter which is known as anti-aliasing filter. Okay, so this is your original information signal, let's say x of t. Okay, so the basic purpose of anti-aliasing filter is nothing but this is you can say this is a low pass filter which will have its bandwidth limited to minus w2 w, which will truncate all the frequency content of the information signal, which will limit to 0 to w hertz. And mind you that you will be deciding the value of w based on depending on the information signal. If there are signals, if there are informations which are useful beyond frequencies of w hertz, then you need to change the filter characteristics themselves. Okay, so this w completely depends on the nature of the information signal. But anyway, to avoid aliasing, practically we use anti-aliasing filter to attenuate all the high frequency components of the signal which are not essential to the information being conveyed by the message signal. Okay, that needs to be understood. Okay, the fine then filtered signal is then sampled at a rate definitely higher than the maximum frequency content. Sorry, if I use w, I can replace this with FM. This is a notation that I've been using all along. Okay, so definitely you'll choose the sampling rate or sampling frequency much higher than twice of FM, which will try to avoid all the aliasing filters. So which will help in actually at the receiver part. So if this is the part with transmitter, say the job of receiver is to demodulate or decode whatever is sent from the transmitter end. So the job of reconstruction filter, say at the receiver end, we'll have another filter which will try to reconstruct the information that is being sent. So this is again a low pass filter which will give you an approximate I can say this is hex hat of t, which represents an estimate of the original transmission that is being sent by the transmitter end. Okay, so this basically reconstruction filter is a low pass filter with a pass band extending from again minus FM to. Okay, then definitely you can say that the original information signal can be reconstructed very faithfully. But if you talk about the characteristics of the filter, you can do certain things. Let me say the output of this. Okay, I'll take this as say g of t. Say there is some information signal, say some random signal which is coming to anti-aliasing filter, which the job of anti-aliasing filter is to truncate the frequency contents and limit all the frequency contents within say minus FM to plus FM, and hence the output of this, the frequency spectrum of g of t, will look something like this, where it will not have any value beyond minus FM to FM. Okay, so this is the frequency spectrum at the input of the sampling block. Then you try to sample this at a rate much higher than the Nyquist rate itself. Then the output of this, if I call the output of this sampling block as a g delta of t, it's a sampled version of g of t, and if I try to plot that particular signal, so it's just a replica of all these, as you have seen now, as you have seen through basic several types of sampling types. Okay, so this will give me replicas of this. One replica will be g of f itself. Okay, one replica would be g of f itself, which is minus fm to plus fm. Next replica would be, just extend this scale, Okay, another would be, since I am setting sampling rate much higher than twice of FM, definitely the other end will not be touching this edge. So definitely if this is 0, Fs will be somewhere here, where the next replica would be somewhere something like this, where this is Fs minus Fm and this is Fs plus Fm, and it goes on. Okay, so two things are satisfied. One is that I have truncated my original information signal and I have limited its bandwidth between minus FM to plus FM, and I have sampled at a rate much greater than the Nyquist rate, which is greater than 2 times of maximum frequency content, which ensured that the adjacent samples are separated enough such that there is no aliasing. There is no crosstalk between the adjacent samples, which is ensured with a two-step of procedure that we have implemented now. Okay, so this is basically G delta of F. The portion which is at the gap, this is actually called as guard band. Okay, so guard band is the band where intentionally we have separated the adjacent samples such that there is no aliasing. Okay, so this guard band, the bandwidth of this guard band, I can write this as, this is simply the difference between these two edges, which is nothing but Fs minus Fm minus Fm, which is nothing but the guard bandwidth is Fs minus twice of Fm. Okay, so what is a good thing about guard band? The guard band ensures that there is no hard design expectation for the reconstruction filter. So if these two were very close to each other, then I had to have such kind of LPF where it might have high edge of rise time and fall time on the LPS of the low pass filter. But the separation with the guard band will ensure a relaxation on the design aspects of the reconstruction filter. So I can have my reconstruction filter or the low pass filter at the receiver. In other words, say if I have a low pass filter, okay, so this is a response of your reconstruction filter, recon, I can say. Okay, this is an important part where this might be useful in your solving few numerical problems. So I can have not infinite fall time edge and slowly rising edge of the filter response and slowly falling edge of the filter response, right? So this would ensure that I can faithfully recover or reconstruct my original information signal without any aliasing or without any taking the samples which is not required to estimate the original information signal. If you want to talk specifically with these edges, this is obviously FM, this is minus FM, okay, and this is you can keep as far as Fs minus Fm, and this you can keep as far as minus Fs minus Fm. Okay, in spite of that, you will not have any aliasing. Okay, so there is so many practical applications of these sampling theorems. Probably this could be one of the initial topics in speech processing or image processing techniques as well, where you need to convert all the analog signals into, say if it's a image signal, you need to convert into pixels, where again it is a discrete in time and discrete in their amplitudes as well. So sampling, quantization and encoding is inherent a part of any system which converts analog signal into digital domain. Okay, this is not just with the communication theory. Okay, so if I can quote any example related, any practical example related to this, which could be your voice signals itself. Okay, if you want to store your voice signals on digital format, sampling of voice signals itself is one of the immediate applications that you may have think of, where as you know that the frequency band of voice signal varies from around say 100 hertz, say around say 3 point around 3 kilohertz. Okay, so usually the audible signal, I mean the range of frequency is much lesser than 100 hertz and much more than 3 kilohertz. But usually as a human perspective, the voice signals are limited to 100 hertz to 3 kilohertz. Okay, so this is adequate in case of telephonic communication purposes as well. This limited frequency band is accomplished by passing the voice signal through a low pass filter, through an anti-aliasing filter first, with its cutoff frequency at 3.1 kilohertz. So first we will send all the voice signals through an anti-aliasing filter. The cutoff frequency of anti-aliasing filter will be around 3 kilohertz, such that it ensures that there is no information which is getting sampled which has frequency components more than 3 kilohertz. Okay, with such cutoff frequency of anti-aliasing filter, say the cutoff frequency of anti-aliasing filter would be around 3 kilohertz. Okay, then we need anti-aliasing filter. We need to do sampling at a rate, usually practically it is around twice of your the maximum frequency content, so it should be around 6 kilohertz. But the standard that is used for your digital voice transmission is around 8,000 samples per second, or it is around 8 kilohertz. Okay, so we can go with a higher rate as well if you want to increase, if you have enough amount of bandwidth, and if you are paying for the price for the bandwidth, then definitely you can increase the sampling rate to retain the quality. But this is one of the initial standards that was introduced for telecommunication, telephonic communication systems. Okay, then obviously there is a transmission bandwidth as well. Say it's around the bandwidth which is used for transmission is approximately around 1.8 kilohertz that you have in your standard telephonic communication systems. Okay, so this is the immediate actual applications of the sampling and the use of anti-aliasing filter to negate the effect of aliasing when it is transmitted over the channel.